In this video, we will have the solutions of some of the exercise problems in section 3.4. The first one is, if U is an ideal of a ring R and 1 belongs to U, then prove that U is equal to R. That is, the ideal U coincides with that of the ring R whenever you have 1 belonging to U. So, for that we first consider, we know pretty well that our U is contained in R. So, this is known to us. What we need to here is R contained in U. So, since U is an ideal of R, U is contained in R, name that as statement 1. Now, for the other inclusion, you consider R in R. Then, just because your 1 belongs to U, that's given to us, by ideal condition that we need to have R into 1, which is equal to R, we have our R belonging to U. So, it's when we say that 1 belongs to U, even if it is not mentioned that R is a ring with unit element, it's understood that this 1 belongs to U is given and U contained in R, therefore 1 belongs to R, which is the unit element. So, 1 being unit element, we have R into 1 to be equal to R, and because U is an ideal, this R into 1 should be present in capital U. And in other words, R belongs to U. So, R in R implies R in U, which means that your R is contained in U. If you name this as 2, from 1 and 2, we conclude that R is equal to U. Now, the second one, if F is a field, prove that its only ideals are singleton 0 and F. In the case of ring, you may have in between these two some ideals, but if it is a field, then you cannot have other ideals than your singleton 0 and F. So, let F be the given field. Then singleton 0 is an ideal of F, that's known. And if you consider U not equal to singleton 0, that is, you consider an ideal which is different from the singleton 0. Now, let that be an ideal of F. Now, to prove that U equals F, we have already said that whenever F is a ring, whenever F is a field, its only ideals are singleton 0 and F itself. Singleton 0 and F. So, we know that this is an ideal. Now, we consider U to be an ideal other than this. So, we have this. Now, if I am able to show that this U equals F, then we can have, that singleton 0 and F are the only ideals. So, if I am able to prove that 1 belongs to U, right, then by the previous problem, U will be equal to F. So, our job is to show that U equals F. So, for that, it is enough we show that 1 belongs to U. Now, we will consider A belonging to U. A different from 0. In U, we shall consider. Now, because A is in U, U being in F, A will be in F. But F being a field, so this implies that A belongs to F. This implies that A belongs to F. Now, because F is a field, A inverse belongs to F. So, because U is an ideal, this element from U and an element from F, so R into U, that's the condition for ideal, R into U should be present in U. So, you have A dot A inverse belonging to U, but A dot A inverse is 1. So, you have 1 belonging to U, and therefore, by the previous problem, U equals F. Next one is, prove that any homomorphism phi of a field is either an isomorphism or takes each element of the field into 0 prime, where 0 prime is the additive identity of the field in the codomain. Now, let F be a homomorphism from the field F to a field, say, G. Or you can even take it as some F prime. Now, we are given that phi from F to G to be a homomorphism. Field homomorphism, actually, we don't have a field homomorphism, any ring homomorphism, field homomorphism, the domain and codomain will be field. But we don't have special condition for that. What we have is ring homomorphism. The condition, what is true for ring homomorphism is true for field homomorphism also. But extra, there is one more thing that ring homomorphism will take identity, additive identity to additive identity. And if we have F and G to be field and this phi is homomorphism, means extra information is that one will be taken to, one is the unit element, that is identity element with regard to multiplication, that will be taken to the unit element. That is the extra condition that will be proved in one of the following problems. But here, as such, there is no name called field homomorphism. Even though we have domain and codomain to be field, the ring homomorphism conditions are only true. Now, since kernel phi is an ideal, whenever we have phi to be a homomorphism, kernel, we can talk about the kernel. Kernel phi is an ideal of F, that is known as. Now, because F is a field and this kernel phi being an ideal, it can either be singleton 0 or kernel phi is F, the whole of F. So, if kernel phi is singleton 0, by the criterion for any homomorphism to be an isomorphism, we have phi to be an isomorphism. If this is the case, kernel phi is the whole of F, then phi takes all the elements of F to 0 prime, because kernel phi is all those elements of F which are taken to the additive identity of the codomain. So, we have the kernel F being equal to F will only imply that all the elements will be taken to 0 prime. So, we have this either phi is an isomorphism or it takes each element of the field into 0 prime. Next we have, if R is a commutative ring and A belongs to R, then this collection AR is an ideal of R. So, in what follows in most of the problems, you will be given a subcollection of the given ring. In some cases, it may be commutative ring, or in some cases, it will only be a ring. So, we need to establish that those subcollections form an ideal of R. So, those types of problems that we are going to have. In that series, we have first AR. A capital R, which is collection of all elements of the form AR, where R range over capital R. So, we know that whenever we want to prove the given collection to be a special substructure or any substructure, we have to describe it and then show that it is non-empty and then check the criterion. Whatever criteria that we have in subgroup, we have only closure and inverse that can be clubbed, and you can simply say that with respect to addition means x minus y. That is enough. In the case of ideal, we have one more condition. For every R and R, U in this subcollection, RU and UR should be in whatever subcollection that we have considered. So, we need to establish, we have to first describe, even though it is given in the problem, we have to write. When we write the solution, first what is given is to be written. So, AR should be described again. This is in the question. So, when you when you write the solution, you have to first give the description of AR. So, AR is what that has to be written. And then you have to prove that it is non-empty. It is non-empty. And then we have to show that it's a subgroup and this condition. Now, since 0 belongs to R, A0, which is, we know that A0 is 0. So, this 0 being a member of AR is non-empty. Whenever we show that any subcollection to be non-empty, it's only the identity element that will be the obvious element present in that. So, how to write that identity element, additive identity, or in the case of group E is the only identity element. So, in that case, we have to see the description of the collection. Then write that identity element according to that. So, that will serve the purpose. So, here AR is non-empty because 0 belongs to AR. Now, you consider two elements U1 and U2 in AR. So, U1 can be written as A into R1. Remember, you cannot change A. A is fixed. Only R, element small r in capital R can only be changed. So, we take it as AR1 and AR2. Now, you consider U1 minus U2. It is AR1 minus AR2. By distributive law, you have A into R1 minus R2. And any element of this form should definitely belong to AR. That's how AR is described. So, AR is a subgroup R under S. Next, we consider R in R and U in this. So, being a member of AR, this U can be written as U equal to AR1, where R1 belongs to capital R. Now, we shall consider UR. U is replaced by AR1 and this R is retained as such. Now, by associativity, we have this to be A into R1 into R. But R1, R are all members of capital R, and therefore this can be named as some R prime, and that's a member of capital R. So because R is a ring, so you have this being of the form AR, that is A small r, something like that we have. But that is how you have the elements of AR. So you have this to be a member of AR, that is UR is a member of AR. And because we have given that R to be a commutative ring, there is no need to specially establish this. Directly we can say that RU belongs to AR. Because R is commutative, we have this to be a member of AR. Now, suppose we want to actually establish, in case that R is not given to be commutative, so we have this to be a right ideal only. See, when you have UR belonging to AR, here we make use of the fact that R is commutative. Only because of that you will have AU. Also, this is RU, sorry. RU also to be a member of AR. So, if that one fails, that is commutativity fails, then you cannot have this to be true. That means your AR cannot be a left ideal, it can only be a right ideal. So, this may not be possible if we do not have R to be commutative. So, for that purpose, we will see how we have established this part. So, RU, which is R into AR1, because U is this, so you have this. Now, associativity is used, so you have RA into R1. Then, commutativity is used here. So, RA is written as AR, and then you have the same thing to be A associativity, A into R1. But R1 you can take it as some R prime. So, your RU is now of the form A R prime. So, it will belong to capital, A capital R. So, you have this to be a left ideal. So, this part gives left ideal condition and this part gives a right ideal. So, if commutativity is not there, then you can have only AR to be a right ideal, AR to be a right ideal if commutativity is not given. Next we have if U and V are ideals. See, this AR plays a very good role in the next section. So AR is an ideal whenever R is a commutative ring, is to be borne in our mind. Now, next problem, if U and V are ideals of R, then we have to prove that U plus V is also an ideal. So again, this subcollection we need to establish to be a substructure, special substructure. So what we need to have description, we have to show it as non-empty, then criterion. So U plus V described, we have described that. Now U plus, to prove that U plus V is an ideal, it is non-empty and it's a subgroup and this condition. So these two together go under criteria, okay, subgroup and then this condition. So to show that it is non-empty, we consider, so we said that already it is an identity element that will serve the purpose. So write that identity element with regard to whatever subcollection that is given to us. So 0 is equal to 0 plus 0. So it belongs to obviously U plus V, because U is an ideal, V is an ideal, they are subgroup, so 0 element will be present in there. Now we consider two elements A1, A2 in U plus V. That A1 can be written as U1 plus V1, A2 can be written as U2 plus V2, where U1, U1, U2 are in capital U, V1, V2 are in capital. Now we consider A1 minus A2, A1 is written, A2 is written. Then because R is abelian under addition, we can interchange, we can take this minus U2 over here and this V1 here. So that you have this, and this is a member of capital U and this is a member of capital V. That is because U and V are subgroups, so these two should be being members of capital U. U1 minus U2 should be present in capital U. So A1 minus A2 belongs to U. In the same way, this is also a member of V. So you have A1 minus A2 to be a member of U plus V. So U plus V is a subgroup under addition. Next, we consider R in R and A in U plus V. We have to show that RA and AR are in capital U plus V. So we should just check whether we are given R to be commutative. We are not given. So that means we have to establish both AR and RA are present in U plus V. So consider AR. A, it is U prime plus V prime that we have taken, or U plus V you can take. So U prime plus V prime into R, and distributive law says that this can be rewritten as U prime R plus V prime R. So this is U prime R plus, this is say some U1 for convenience sake. You have this to be U1 and this as V1. Now this U prime R, because capital U is an ideal, we have that to be right ideal. So this must be present in capital U. And again, because capital V is an ideal, this must be present in capital V. So you have AR to be present in U plus V. And in the same way, R into say some this A is U prime plus V prime. So you have this. Again, using distributive law, you have this step. Again, because U is an ideal, this is a member of U. V is an ideal, so this is a member of V. So RA is a member of U plus V. So U plus V is an ideal.